Mars, a celestial neighbor draped in shades of rust and crimson. For centuries, humans have gazed upon this red beacon in our night sky, pondering its secrets. Today, powerful telescopes reveal tantalizing details of a world both familiar and alien. Our fascination with Mars is deeply ingrained. It represents the ultimate frontier, a challenge to our understanding of life itself. Could this desolate world once have harbored life? Could it still? Each image from rovers, every analysis of Martian soil brings us closer to understanding our place in the cosmos. Mars is a planet of stark contrasts. A celestial enigma wrapped in layers of intrigue. It is a world of desolate beauty, where towering volcanoes cast long shadows across barren plains. Vast deserts, sculpted by ancient winds, stretch towards the horizon. Evidence of ancient rivers and lakes etch themselves onto the Martian landscape. These ghostly remnants hint at a time when water flowed freely across its surface. Swirling dust storms, some so large they engulf the entire planet, rage across its surface. Mars invites us to explore, to unravel its riddles and confront its challenges. As we embark on this journey of discovery, one thing is certain: Mars will continue to surprise us. Mars is a study in contrasts, a celestial dichotomy that both attracts and repels. In the cold vacuum of space, it stands as a monument to both the power of nature and its unforgiving indifference. On the one hand, Mars shares similarities with our own Earth. Its days are only slightly longer, marked by the familiar cycle of sunrise and sunset. It experiences seasons, albeit more extreme due to its elliptical orbit. And its polar caps, like Earth's, expand and contract with the rhythm of the Martian year, yet any resemblance to our home planet ends there. Mars is a world stripped bare, its surface a canvas painted in shades of rust and ochre. The air, thin and unbreathable, offers no protection from the harsh radiation that bombards the surface. Water exists mainly as ice, locked beneath the surface or trapped in the polar caps. Features etched into the Martian landscape tell a story of ancient floods and colossal volcanic eruptions. The surface of Mars is a chronicle of its ancient past, a testament to the power of water to shape landscapes. Vast canyons, dwarfing anything found on Earth, scar the planet's face, carved by rivers that flowed for millennia. Elsewhere we find evidence of ancient lake beds, their smooth sedimentary floors a stark contrast to the surrounding rugged terrain. Orbiting spacecraft have detected vast reserves of water ice locked beneath the surface, particularly in the polar regions. There is evidence of seasonal flows of briny water seeping down crater walls and leaving dark streaks in their wake. These recurring features suggest that liquid water, however salty and ephemeral, may still exist on Mars today. Where there was water, there could have been life. The possibility of subsurface aquifers is a tantalizing prospect. The Martian atmosphere presents a paradox. It is both a whisper and a roar. Compared to Earth's protective blanket of air, the Martian atmosphere is a mere wisp, barely 1% as dense. This thin veil offers little protection from the sun's harmful radiation. Yet, despite its tenuous nature, the Martian atmosphere is capable of producing weather phenomena that dwarf anything seen on Earth. Dust storms, driven by the planet's extreme temperature gradients, can erupt with astonishing ferocity, engulfing entire continents in a matter of days. These storms, sometimes lasting for months, can blanket the planet in a reddish haze, obscuring the surface from view. These dust storms may actually play a crucial role in the Martian climate. Understanding these complex processes is essential if we ever hope to unravel the mysteries of the Martian climate and its potential for supporting life. The question of water on Mars is not just a scientific curiosity, it is a profound inquiry into the very nature of life beyond Earth. The red planet holds within its dusty embrace tantalizing clues that hint at a much wetter, potentially life-supporting past. Scientists have spent decades analyzing images, data, and samples, all searching for the answer to a fundamental question. Did Mars, once upon a time, harbor oceans, lakes, and rivers that flowed with liquid water? The answer is complex and multifaceted. There is a growing body of evidence that points toward a watery past. These clues are etched into the very fabric of the planet. The search for water on Mars is a journey into the heart of the red planet. It is a journey fueled by curiosity, driven by the desire to answer one of humanity's most enduring questions. Are we alone in the universe? Imagine standing on the edge of a canyon so vast, so grand, that it dwarfs anything found on Earth. This is Valles Marineris, a scar across the face of Mars so large it could stretch from New York City to Los Angeles. Carved by forces that raged billions of years ago, Valles Marineris is not just a canyon, it is a testament to the power of water. The sheer scale of this geological marvel, its winding channels and towering cliffs, speaks to a time when rivers flowed freely across the Martian surface. Across the Martian surface, we find a network of similar features: dry riverbeds, meandering channels, and deltas. These ancient waterways whisper tales of a bygone era, a time when Mars may have been more akin to Earth. Analysis of Martian meteorites reveals the presence of minerals that form in the presence of water. These minerals provide further confirmation that liquid water once interacted with the Martian surface. While the surface of Mars may now be a frozen desert, the red planet holds on to its watery past in the form of ice. Vast reserves, locked beneath the surface and hidden within the polar ice caps, represent a tantalizing glimpse into the potential for Mars to harbor life-sustaining resources. These icy reservoirs are not merely frozen relics, they are a testament to the enduring power of water to persist. The polar ice caps, visible even from Earth-based telescopes, are the most obvious manifestation of this frozen treasure. Composed primarily of water ice, with a seasonal frosting of carbon dioxide, these caps wax and wane with the rhythm of the Martian seasons. Data from orbiting spacecraft have revealed vast deposits of water ice lurking beneath the surface. These subsurface ice deposits represent a significant reservoir of water. Their presence has profound implications for the search for life on Mars. Perhaps the most intriguing and unexpected discovery in recent years is the evidence for liquid water, however fleeting, on the surface of present-day Mars. This evidence comes in the form of recurring slope lineae, dark streaks that appear seasonally on certain slopes. These recurring slope lineae suggest the presence of briny water flowing just beneath the surface. The leading hypothesis suggests that they are formed by the melting of subsurface ice during the warmer months. This briny water then seeps to the surface, creating the distinctive dark streaks as it flows downhill. The presence of liquid water on Mars, even in this ephemeral and salty form, has profound implications for the search for life. On Earth, wherever we find liquid water, we find life. They raise the tantalizing possibility that extremophiles could exist in these brines. The question of life on Mars is not merely a quest for alien microbes. It is a profound inquiry into the very nature of life itself. Could life, in some form, have arisen independently on a neighboring planet? The search for life on Mars is a search for a signature, a telltale sign that life has left its mark on the red planet. This signature could take many forms. Fossilized remains of ancient organisms, chemical traces of biological processes, or even the detection of microbial life itself. Each new mission to Mars brings us closer to answering this fundamental question. The challenge lies not only in finding evidence of life, but also in interpreting it correctly. Mars is a master of mimicry, its geology capable of creating features that can easily be mistaken for signs of life. Rocks can be sculpted by wind and water into shapes that resemble fossils, and chemical reactions can produce organic molecules that raise false hopes. The human mind is wired to find patterns, to see order in chaos. It is this instinct that leads us to discern faces in clouds, animals in star constellations, and perhaps fossils in Martian rocks. The search for fossilized evidence of life on Mars is a tantalizing but treacherous pursuit. Several images beamed back from Mars rovers have ignited the public imagination, showcasing intriguing shapes and structures. These Martian fossils have sparked heated debates within the scientific community. The difficulty lies in the fact that fossilization is a rare process, even on Earth. For an organism to be preserved as a fossil, a specific set of conditions must be met. On Mars, the odds of fossilization are even slimmer. In the annals of Mars exploration, the Viking missions of the 1970s hold a special place. These twin landers, the first to successfully touch down on the Martian surface, carried with them a suite of instruments designed to search for signs of life. The results of these experiments, however, remain a source of controversy and debate to this day. One experiment, the labeled release experiment, yielded particularly intriguing results. This experiment involved adding a nutrient solution tagged with radioactive carbon to Martian soil samples. The idea was that if microbes were present, they would metabolize the nutrients and release radioactive carbon dioxide, which could be detected by the lander's instruments. To the surprise of many, the labeled release experiment did detect a release of radioactive gas, suggesting the presence of microbial activity. However, other experiments on board the Viking landers failed to find evidence of organic molecules, the building blocks of life. This discrepancy in results has led to decades of debate, with some scientists arguing that the labeled release experiment did indeed detect Martian life, while others maintain that the results can be explained by non-biological chemical reactions. In the search for life beyond Earth, organic molecules are the holy grail. These carbon-based molecules are essential for life as we know it. Finding them on Mars would be a highly suggestive clue. Recent missions have made significant strides in detecting organic molecules. The Curiosity rover found complex organic molecules in ancient mudstone deposits. These findings suggest the building blocks of life were present on early Mars. Even in its stillness, Mars possesses an unsettling power. A quiet menace lurks beneath the thin, cold air. This is the fury of the dust storm, a phenomenon unique to the red planet. On Mars, they are planet-altering events, shrouding the entire globe in a veil of red. The first sign is often the appearance of dust devils, swirling vortices of dust. These dust devils can act as seeds, feeding into larger storm systems. As a Martian dust storm gathers momentum, it transforms into a planet-encompassing event. Driven by winds up to 60 miles per hour, the dust engulfs everything. The sky turns a sinister red as iron oxide dust blots out the sun. On the ground, disorientation and isolation prevail. Familiar landmarks vanish into the swirling dust. The sun, a pale disk, casts no shadows, creating an endless twilight. The air, thick with dust, takes on a metallic tang, and the silence is eerie. For robotic explorers, dust storms are both dangerous and opportunistic. Dust coats solar panels, reducing power and forcing low power mode. Fine particles clog instruments, threatening their operation. However, dust storms offer a unique opportunity to study the Martian atmosphere and its dynamics. The driving force behind Martian dust storms is a complex interplay of factors, a delicate balance of atmospheric conditions, surface properties, and even the planet's orbit. Understanding this engine of chaos is essential for predicting the onset and severity of dust storms, which is crucial for both robotic and, one day, human exploration of the red planet. One key factor is the Martian atmosphere itself. Its thinness, combined with its low thermal inertia, means that the atmosphere heats up and cools down rapidly in response to changes in solar radiation. This creates significant temperature differences between the equator and the poles, as well as between day and night, driving powerful winds that can loft dust into the atmosphere. The surface of Mars, covered in loose powdery regolith, is also a contributing factor. This fine dust, the product of billions of years of weathering and meteorite impacts, is easily lifted by the wind, providing ample fuel for dust storms. The topography of Mars, with its vast plains, towering volcanoes, and deep canyons, also plays a role, influencing wind patterns and creating areas where dust can be trapped and concentrated. Section 4. Dust, the architect of a world. Martian dust storms are a fundamental part of the planet's climate system, shaping its environment over time. They influence everything from temperature to atmospheric composition. Dust particles absorb sunlight, warming the atmosphere. This effect is most pronounced during global dust storms. Dust storms also transport water vapor, impacting the Martian climate. Section 1. The Methane Mystery, a Whisper of Life. The detection of methane on Mars is profound, suggesting the possibility of life. On Earth, methane is mostly produced by microorganisms called methanogens. Could Mars harbor hidden ecosystems, perhaps in geothermal vents or underground water? Section 2. Seeking the Source, a Tale of Two Origins. The presence of methane on Mars has ignited a quest to unravel its origins and determine if it holds the key to Martian life. Two main hypotheses have emerged, biological and geological. The biological hypothesis suggests methanogenic microorganisms in the Martian subsurface. The geological hypothesis posits methane from abiotic processes like serpentinization. Both hypotheses offer profound implications for our understanding of Mars. Methane on Mars fluctuates, showing seasonal variations and sporadic spikes. Higher methane in summer suggests a possible biological source. Geological processes also vary seasonally, affecting methane release. Sporadic spikes suggest dynamic sources like underground reservoirs. The mystery of Martian methane has profound implications beyond Mars. The search for life hinges on detecting subtle clues and distinguishing life signatures from abiotic processes. Mars serves as a testing ground for understanding life's universality. Determining Martian methane's source offers insights into planetary habitability. Studying Martian methane informs our understanding of Earth's climate. Methane is a potent greenhouse gas, contributing to climate change. Studying methane on Mars helps us mitigate climate change on Earth. In the vast emptiness surrounding Mars, two celestial companions dance a silent waltz around the red planet, Phobos and Deimos, the Martian moons. These diminutive worlds, more akin to asteroids, stand in stark contrast to Earth's moon. Named after Greek gods, Phobos and Deimos were discovered in 1877 by Asaph Hall. Their irregular shapes and cratered surfaces hint at a tumultuous past. Were they captured asteroids or remnants of a giant impact? Of the two Martian moons, Phobos is the larger and closer to its host planet, a celestial wanderer trapped in a death spiral. Its orbit, just 6,000 kilometers above Mars, completes in under 8 hours. Mars' gravity pulls Phobos closer, dooming it to a fiery demise. Scientists estimate that in millions of years, Phobos will crash into Mars or form a debris ring. Deimos, a small, distant moon, orbits Mars from afar. Its stable orbit is over 23,000 kilometers away. Deimos may eventually escape Mars' gravity. Named after the Greek god of terror, it evokes serenity. Deimos' smoother surface suggests a thicker regolith layer. It may be a captured asteroid. Studying Deimos helps us understand the Martian system. The human mind often seeks extraordinary explanations for the unknown. Some propose Phobos is an artificial structure, perhaps a derelict spacecraft. This hypothesis is based largely on speculation. Proponents point to Phobos' unusual orbit and low density. The scientific community remains skeptical. Most scientists agree Phobos' characteristics are natural. Its low density is likely due to its porous composition. The grooves are likely stress fractures from tidal forces. The artificial moon hypothesis remains unproven. It reminds us of the vastness of the unknown. As we stand on the precipice of a new era of space exploration, with our sights set firmly on Mars, it's perhaps fitting to reflect on what draws us to this distant, enigmatic world. Is it simply the thrill of discovery, the desire to push the boundaries of human ingenuity and daring? Or is there something deeper, more profound, that compels us to reach across the vast gulf of space and set foot on another planet? Mars, for all its alien beauty, is a reflection of ourselves. A celestial mirror reflecting back our hopes, our fears, and our enduring quest to understand our place in the cosmos. In its rusty hues, we see the colors of our own sunsets, a reminder of the shared cosmic dust from which both planets were born. In its ancient riverbeds and canyons, we see the echoes of Earth's own geological past, a hint that the forces that have shaped our planet are not unique to us. But Mars is also a stark reminder of our own planet's fragility. Its thin atmosphere, its barren landscape, its lack of liquid water, all serve as a cautionary tale of what could befall Earth if we fail to care for our own planetary home. The challenges of surviving on Mars, of extracting resources, generating energy, and creating a habitable environment are a mirror reflecting back the challenges we face on Earth as we grapple with climate change, resource depletion, and environmental degradation. As we stand on the precipice of a new era of space exploration, with our sights set firmly on Mars, it is perhaps fitting to reflect on what draws us to this distant, enigmatic world. Is it simply the thrill of discovery, the desire to push the boundaries of human ingenuity and daring? Or is there something deeper, more profound, that compels us to reach across the vast gulf of space and set foot on another planet? Mars, for all its alien beauty, is a reflection of ourselves, a celestial mirror reflecting back our hopes, our fears, and our enduring quest to understand our place in the cosmos. The exploration of Mars is a testament to the enduring human spirit, our innate curiosity, and our relentless pursuit of the unknown. From ancient astronomers to modern-day scientists, we are drawn to Mars. The call of the cosmos beckons us to venture beyond the familiar, to explore, discover, and understand. It is calling us to Mars. The story of Mars is still being written. Each new mission adds a new chapter to this unfolding saga of exploration and discovery. We've only just begun to scratch the surface of its secrets. Did life ever exist on Mars? Could it still exist today? The next chapter will be written by human explorers. The first human footprints on Martian soil will mark a pivotal moment in human history. These pioneers will face challenges unlike any humans have ever faced before. But the rewards extend far beyond scientific discoveries. By venturing to another planet, we will gain a new perspective on our place in the universe. We will come to appreciate the preciousness of our own planet and the importance of safeguarding our future. The exploration of Mars is not a destination, it is a journey that transforms our understanding of the universe and ourselves. As we venture farther into the cosmos, we carry lessons about resilience, exploration, and curiosity. The future of Mars exploration is bright with promise. New technologies and international collaboration will be essential, but the human spirit will ultimately determine our success.